I've been studying colors in a pandemic. Isaac Newton did the same during the Great Plague of London, when he famously laid out red, orange, yellow, green, blue, indigo, and violet as the colors of the rainbow. Maybe you were even taught ROYGBIV in school. Well, if you'll pardon my aggression, I think these colors are completely inane. And before the video ends, I plan to kill this man named Roy and rifle through his pockets for loose change. Maybe I can convince you to join me. My stance is all backed up with scientific and linguistic evidence, but I do have a bit of an agenda. That agenda is this: indigo does not belong in the rainbow, and cyan does. So yeah, despite the evidence, maybe it's most apt to say that my color opinions, as expressed here, will all be based on science. Newton, while sheltering in place, experimented with a glass prism and named the colors he saw on the electromagnetic spectrum. The thing is, Newton admitted himself that he might not have had the greatest color vision. He only saw 5 at first, but later added on orange and indigo, because he thought, along with the number of musical notes in an octave, that having 7 colors specifically would be more divine. In the end, the number of colors we decide to have is pretty arbitrary. It's been centuries since Newton died, so maybe we ought to let some of his ideas rest. We can take calculus and leave the others, you know. It's also entirely possible that when Newton wrote down blue, he was really looking at the brighter cyan, and when he wrote indigo, he was really looking at the darker blue, close to violet. Indigo these days has a rather nebulous meaning anyway. What even is indigo? Is this indigo? Or is this? It's certainly not this, because that's magenta, and it doesn't belong in the rainbow either. Magenta is what our brain interprets when red and blue overlap, but it's not anywhere on the rainbow you'd see from a prism. It doesn't have a wavelength of light like the others do. For this reason, if we're talking purely about wavelengths of light, cyan makes more sense to include in a ROYGBIV acronym. Cyan is also practical because it allows us to split blue into 2 parts. The new cyan can encompass a similar amount of shades as yellow and orange do. At risk of sounding like Newton, cyan would also balance out the rainbow nicely, since it keeps 3 colors on each side of green, and green is roughly the center of our visible spectrum. There are more reasons to consider cyan for inclusion, but first, we need to talk about the illusion behind primary colors. Sometimes, teachers tell lies. They do in America, at least, because I was taught that red, yellow, and blue are primary colors, and that combinations of these 3 can mix any other color. This is all fine and good if you're limited in your art supplies, because I don't think anyone expects to recreate the entire range of human vision with a pack of crayons. But the thing is, red, yellow, blue, RYB, has been outdated for centuries. These days, we use red, green, and blue, or RGB, on our TV screens and computer monitors because it's possible to mix far more colors with red, green, and blue than it is with red, yellow, and blue. More on why that is later. In the RGB system, the 3 primaries put together make white light. Combining just 2 of the primary colors gives you secondary colors. As you can see here, magenta, yellow, and cyan are formed, meaning that these are the secondary colors in the RGB color system. It goes even further though. While RGB is the system for mixing light, the system for mixing paint is CMYK, which is just the inverse. Red, green, and blue are the secondary colors in this system, and the primaries, CMY, mix to black, just like real paint would. As it turns out, this is really all complementary colors are, inverses of each other, so that when mixed, they cancel out to grayscale. Cyan is both the inverse and the complement of red, which is why these 2 colors are useful in 3D glasses. Since it's vital to our best set of primaries, it stands to reason that cyan deserves a spot in the rainbow. But the truth is, even with CMYK and RGB, any set of primary colors is going to run into a problem somewhere, so long as you're trying to display every single color humans can see. Unless you're colorblind, most of us have 3 types of cones in our eyes, and these cones are sensitive to different wavelengths of light, which roughly line up with the RGB system. Each one gets most excited roughly around one of the primaries, red, green, and blue, but we're able to see color a tiny bit outside these peaks too. Plus, we're able to see colors that aren't even in the electromagnetic spectrum, like I mentioned earlier with magenta. So if you try to use mixtures of just 3 colors, you might come close, but you won't be able to recreate all of human vision. Because of how complex this is, there have been attempts to accurately plot out our color vision, the most widely accepted of which being as if normal math wasn't hard enough, physicists invented color math. One of our best approximations of color looks like a lumpy triangle. It represents all the possible hues at their highest possible saturation, or intensity. Here, it's a lot easier to tell why RGB is better than RYB. If we pick 2 points on this graph, then draw a line between them, we can get any of these colors on the line just by mixing different amounts of the 2 original points. Therefore, if we have 3 points, we can mix any of the colors along the lines of the triangle, but also any of the colors inside the triangle. This here is the red, yellow, blue, or RYB triangle. But compare this to the red, green, blue, or RGB, and you'll find that RGB has a wider range, or gamut. Why don't they make an even bigger triangle? Well, this covers pretty much all the visible colors. If you wanted even more, you'd have to set the points to be outside our range of vision, at imaginary colors. But I digress. So long as we stay within the realm of humanity, RGB is clearly superior, and cyan plays an integral part. I don't blame anyone for not accepting the gospel of cyan sooner, though. We simply didn't have the framework yet, in math or in language. Compared to other colors, cyan can be fairly rare in nature. Beyond the aqua of a clear spring or a light sky, there aren't many naturally cyan objects, and almost no cyan flowers, except in old-school Minecraft, and maybe if you count certain forget-me-nots and begonia leaves. These ones here aren't even that cyan, and they're just plastic from Dollar Tree. Humans are typically better at distinguishing between green, yellow, and red shades rather than blue, which may further explain our ignorance surrounding cyan. 2 of our 3 cones have peak sensitivities right next to each other. This might have made us better at distinguishing the greens to reds of ripening fruits, and the red tints of the human body. Either way, we're worse at distinguishing cyan and blue, and they appear less as objects in nature, meaning that we've had less of a reason to label and point to them. For example, languages with only a few basic color terms tend to combine green and blue into one term, if they have such a term at all. In the World Color Survey, a study of 120 unwritten languages, there were no dedicated terms for blue in languages with less than 5 basic colors. This occurs even in languages that greatly differ from traditional English models. In the Dani language, there is a term for light colors, such as yellow and white, a term for red, a term for dark colors, and a term for grue. There is even a language with only 2 terms, one for all the light, warm colors, and one for all the cool, dark colors. With all this linguistic variation, there's much debate over how universal colors actually are. While all non-colorblind people probably see colors roughly the same, those who speak languages with fewer color categories are less likely to perceive as many clear boundaries between colors. Additionally, there are some languages, such as Russian, that discriminate between light and dark blue. So really, all I'm proposing is that we adopt this with cyan and blue in English. My hypothesis is that if I raised 2 twins and constantly pointed out cyan to one of them while keeping the other as a control, the cyan kid would have an easier time distinguishing and identifying cyan than their typical American twin. But unfortunately, I don't have the patience to raise 2 children just on a hunch. I'll settle for telling you that if you stay diligent, you might start to recognize cyan in places you never had before. In conclusion, ROYGBIV sounds awful, so we're going to have to kill Roy altogether. We can make a mnemonic along the lines of, "Please excuse my dear Aunt Sally." Cyan makes a good candidate for inclusion in the rainbow, based on all 3 models I outlined. RGB, CMYK, and the spectrum of pure wavelengths. I call upon you, the viewer, to spread the good news. Go aggravate your friends with it, start a grassroots movement, and maybe we'll make t-shirts. I've got a video on types of light in space photography if you're interested. And in the future, I'm planning to make more videos about all the light and color facts that I couldn't fit into this one. Maybe color blindness and synesthesia. So let me know in the comments if there's anything you'd like me to cover. Custom-made cyan snow cone. That's all.